All right. Hi, everyone. I hope you're all doing great. Can you all hear me in the back? Yep. So do you have any questions about the previous lectures? So the lectures I gave on wavelet representations? No questions about this? So, sorry, was that? You had a question? Oh, OK. So one motivation for the previous lectures I presented was to be able to deal with the case of irregularly observed time series. And that's something I will come back to in Thursday's lecture. Before I start talking about estimation in the context of irregularly sampled time series, which is clearly something that is more difficult to deal with than regularly sampled time series, I'm going to really focus on the very procedure that we use to estimate parameters in a statistically sound manner, and in particular how in the setting of time series analysis we may deal with situations where the fundamental law of large numbers does not work anymore, simply because there is such persisting correlation through the time series. Because there is no property of asymptotic independence, you can no longer rely on different experiments so as to use them as independent experiments. Basically, you need to pre-process your data, for instance, in a certain way so as to enforce this asymptotic independency. And if you don't, there are many unusual things that will happen. Namely, well, the variance of your average-based estimator will not vanish as you add more samples to your data set. In fact, in some cases, it may explode. And that may lead you to very radically wrong conclusions if you do not verify that your time series is actually short-range dependent and use techniques that were primarily designed for time series that abide by this assumption. So one modern consequence of having overlooked these issues of long-range dependence and not deemed them worthwhile paying attention to was, according to some experts, the crisis of 2008 on financial markets. At least it's responsible for bad risk management practices that had become pervasive in the banking system. And largely because the models that risk managers were using completely forgot that the time series of interest on stock markets were not, did not have the memory properties that they assumed, and therefore they, in reality, had a different behavior from what was predicted in risk assessment models. And so one voice that really contradicted the dogma at the time in terms of risk management or even pricing was the voice of Benoit Mandelbrot. So you may know him for having invented the theory of fractals, or at least being a huge contributor to this theory. In fact, Benoit Mandelbrot, when he was working at IBM, was fascinated by financial time series. So at some point, the CEO of IBM gave him the chart of the price of IBM, just an end-of-day price chart, so very low resolution, and asked Benoit Mandelbrot if he could find something to say about this data. And Mandelbrot had a radically different view on this data set if you compare that to the studies that were conducted by a specialist of financial time series. First of all, Benoit Mandelbrot saw the time series of prices as a fractal. Which is something very different from the theory that many people have developed in finance, which basically assumes that this time series, the price of a certain stock, is roughly Brownian or has a very strong relationship with the Brownian motion. So he did really use a radically different model, and that led him to different conclusions. One of the conclusions he came to was, and this is better described in a more technical book called Fractals and Scaling in Finance. This is more of a high-level book that I'm presenting to you today, so the misbehavior of markets. So here, Benoit Mandelbrot explains that one of the things that he did not agree about the models that were used in finance was that the variation of price do not follow a Gaussian distribution, and also they don't have the independent the independence properties that were assumed in the very first models that were developed by Bachelier and then used, for example, by Black and Scholes to devise a very precise pricing theory. And he predicted that one consequence was that the behavior of such financial time series, because you no longer have this independence of increments, was much more turbulent than what was predicted. And so, so I'm just trying to look for the very sentence where he mentions that. Sorry. I could not highlight this thing for some reason. This is not working really well. Yeah, so here it could, oh, sorry, I'm just trying to, okay. All right, that works. Yeah, so here he says basically that one aspect that has been overlooked by the founders of pricing theory is a higher turbulence than they expected, and also shocks such as so price jumps, or also catastrophic events such as bankruptcy. And so that's typically something that is tightly related to the topic that I will mention today, so long-range dependence, and shows us that if we're studying a time series, we need to be very careful about the degree of turbulence and long-range dependence, therefore, that it features. One very important topic related to that matter today is that of assessing whether there is a causal relationship between CO2 emissions and its concentration in the atmosphere, therefore, lately. So this is basically our starting to release large amounts of CO2 in the atmosphere of the Earth, and the corresponding average temperature throughout the globe. And beyond the political controversy that there is about climate change, there is in fact a very statistical and very principled controversy, a discussion between researchers about how we can assess whether there is indeed a statistical meaningfulness to this recent parallel trends we see in the concentration of CO2 and the temperature of the lower atmosphere. And in fact, it's really not a trivial question. And the reason why it's not trivial to basically, I mean, the method that you can use is really not taking a look at these two time series, say that the levels basically go up at the same time, and so there is a certain level of correlation, and then use this correlation to say, hey, there is really a relationship between the concentration of CO2 and the temperature of the atmosphere. This does not work, because if you were to basically compute this correlation as an average computed over this series of points, you would completely overlook the fact that within each of these time series, there is a certain degree of autocorrelation. There is no asymptotic independence, so there is a certain memory within each time series, which means that you should probably not rely blindly on an estimator of correlation that relies on an average to concentrate about a certain quantity which you think corresponds to the actual amount of correlation there is between those two time series. Okay? So I will precisely describe today what I mean by long-range dependence and the consequences there are when we overlook such features of our data sets. So the problem with long-range dependence, as you've probably noticed already, is that the stakes seem extremely high. We're talking about huge financial crisis, the kind of which we had never seen before, and also elements that can have a primordial role as to whether our species will survive the centuries to come or not. So one reason why it is so hard to talk about long-range dependence is that although the stakes are really high, it's very hard to pinpoint the very statistical mechanisms that no longer work when we study time series that do not provide asymptotic independence of serial observations. So today I will show you a couple of very basic numerical experiments so as to raise an alarm in terms of what we can ask average-based estimators to do and what we cannot expect them to do, and basically in which settings the law of large numbers will really not work out for us. After that, I will show you that there is a regime in which you may have a time series that is second-order stationary, so not something like a Brownian motion, which is not. And yet this time series can have a long degree of memory. It can be long-range dependent, and therefore if you do have a strong case for trying to estimate a second-order stationary structure for this time series. However, as you try to do that, and if you rely naively on the law of large numbers to do so, your estimators are not going to converge. So they will become completely unreliable. And so, yeah, one reason why it's also kind of hard to talk about long-range dependence is that the formalism is extremely recent. In fact, the really first well-principled and clear exposition of the topic has been written just this year, so in 2017. It's a very recent book that I based this lecture on. Before that, you had basically to read through scattered articles or read through a previous monograph, which was really not as clear and really did not show problems related to the explanation of what long-range dependence is, such as the fact that, in fact, there are 5 non-equivalent definitions. Actually, there should be an S here. Definitions of long-range dependence. So already you can see that this is not an easy topic to talk about if there are 5 elements that correspond to the intuition we have about what long-range dependence should be. And although they are related one to another, they are not all equivalent. So after that, I will show that there are modeling opportunities related to long-range dependent features, and therefore there are ways of capturing long-range dependencies in your time series. Thanks, for example, in the first place to FARIMA models, which are an extension of ARMA models to the setting of long-range dependent time series. And finally, I will show you that although concentration may occur, so as you average out observations, and you hope that the law of large numbers will work out for you. In some settings, although there is a degree of long-range dependence, that may still be the case, but the form of the distribution, so basically the distance you will have in probability to the actual parameter will not follow a Gaussian distribution. It will follow something else. So that's another consequence of having these this absence of independence. You will not have the gentle cancellation of perturbations that led to a very concentrated Gaussian distribution. Okay, a Gaussian distribution has a lot of its weight about its mean. Okay, here we'll quickly have, for example, fat tail distributions, which will offer a limit low for your average of interest, but will feature a fat tail, which is a behavior that is radically different and has different implications in terms of risk if you compare that to a Gaussian distribution. So that's what we'll see today. And I will start with very simple examples to show you that, in fact, in most cases, although we have a certain degree of autocorrelation in a time series, we're still OK. And the example I'm going to show you is just based on an AR1 model. So I generate a time series like that. I use a Gaussian noise, so I'm not using the distribution of the noise to create any problems here. I use a very gentle Gaussian distribution, nothing particular about that. And in this setting, if the noise is centered, I can expect this process to be second-order stationary and also have always the same mean, 0. And so I can try to compare the empirical estimator for this average with its actual value. And so anytime I compare this estimator in value with respect to 0, I get an idea of how, as I increase t, for example, I will have a tighter distribution for this estimator about its mean. The other question that I will try to answer is the influence of this rho parameter here. So it's natural if, for example, I set rho to 0, that all the observations I have here being IID, this quantity here will follow the central limit theorem. So it will concentrate to 0, and it will also have a Gaussian distribution. And as I increase t, I will tighten the variance of this distribution. What happens, however, is that as I increase rho, well, here in this very setting, we'll see that the spread of the distribution will be slightly higher. And there is a breaking point, typically when rho is equal to 1, where concentration, in fact, does not occur anymore. Okay, and we really don't benefit from the denominator t here in terms of lowering the magnitude, the variance, sorry, of this estimator. So just to make things concrete here, I generate a bunch of time series, all independently one from another. For each time series, I compute this empirical average, and then I plot the distribution of these averages here. Actually, yeah, this is a, yeah, that's fine. So I have 2,048 trials, okay, and that's how I have this distribution, which has basically 248 independent points for my estimator. So what happens when rho is 0, as promised, is that as I increase t, well, the variance of this limit distribution here decreases. Okay, so basically the law of large numbers is working out for us, and also the central limit theorem, and everything works fine. We can rely on these two very basic rules of statistics to enable us to discover actual properties of the world, although we only get to observe it through finite data sets. So now I can play around with rho and, for example, increase this level of autocorrelation slightly. And here we can see that as rho is 0.1, we're still mostly okay. So the concentration still occurs, and there are a lot of theorems, for example, in classic books of time series analysis, such as the Brockwell and Davis, that will tell you that, yeah, if that's the case, although you have an autoregressive process here, because it's just an autoregressive process and it has a short-range dependence, you can expect concentration to occur for this estimator. That's also true if you have anti-correlation. In fact, you could expect that the variance is going to shrink even faster. And then as you increase rho, well, you can see that the convergence is slower, but it still occurs. So that was the problem. Same thing if I have a strong anti-correlation. Well, the problem is that if I set rho to 1, well, I deal with the time series, which is a Brownian motion. And what happens in your Brownian motion is that no perturbation ever gets forgotten. Okay? If I go back to this relationship here, I set rho to 1. Any change of value at any point in time for the perturbation will affect all the following values of the Brownian motion forever. There is no vanishing correlation. Therefore, we cannot expect at all to have this asymptotic property of independence that helped us apply the law of large numbers, although there was a certain level of autocorrelation. So here, everything breaks down. And to a certain extent, it's expected. After all, when we study a Brownian motion, we study a time series whose variance will go linearly with a t, with the time, and therefore we don't even have the assumption of second-order stationarity here. So in fact, we're probably not using the right tools, or even the right, we're not even setting the problem right when we do that, okay? Unfortunately, there is a regime that lies between this Brownian motion in terms of amount of memory and these gentle autoregressive processes that will create a lot of issues. And so that's this region here will be the topic of today. Another, so that's just to show you that as you manipulate rho and you increase the number of samples, everything works well, except if you have a unit root. Okay, if your rho is 1 here, you have this Brownian motion that makes everything break down. So that's just the estimation of the mean. As I was saying here, we're interested in second-order stationary time series, and so one estimator of interest is, in fact, the covariance estimator. And there, as you would expect, the issues, I mean, the properties that were true for first-order estimation are also true for second-order estimation here. For example, if we have the covariance between x and y. And so we still have concentration, although there may be some degree of autocorrelation or anti-correlation. And if we have unit roots now, if we take these two Brownian motions, we generate them independently, one from another, but we compute the covariance of x with y. Well, this covariance, which is in fact 0, has an estimator which will have a huge spread in distribution. And so it's funny, you can actually try that out on your laptop, generate two independent Brownian motions, compute the covariance or the correlation of the two. And for example, in terms of correlation, it's really, it's not rare at all to find 0.8 as a value of the estimated correlation between two processes that are in fact independent. And that's just because this concentration, we would hope, would work for the estimator we use for the correlation, does not occur anymore, simply because we no longer have independent experiments. So in fact, we no longer accumulate knowledge from different samples, actually. The samples are too closely related to enable generalization of any rule that we would observe. And here you see as well that the variance of the estimator decreases if we have an autoregressive model without a unit root. And as soon as we have a unit root, well, everything breaks down. So as I was saying here, it's a bit ridiculous to try to estimate this covariance in the univariate setting for a Brownian motion, as you know that you don't have second-order stationarity. However, there is a case in which some researchers that were, very good researchers in the field of econometrics started to do things that made, in fact, no statistical sense because concentration was not occurring. So one thing you can do is take a certain time series of stock prices, for example. You don't have to have a fine resolution. You can take end-of-day data. So you take something about a time series, say, for, I don't know, Apple, okay? And then you can find another time series in the real world that follows, that has a long memory. And it turned out that examples of these were, for example, the amount of rain in a certain state, okay? So this is not really a Brownian motion, but it still has this absence of asymptotic independence of observation. And so what happened is that some quantitative researchers in finance tried to build a regression model of, say, could I explain the price of Apple with a linear model like this, okay? And the procedure they used to estimate A was just by OLS, so ordinary least squares. And what you will find in these settings is that if you compute the R square of this ordinary least squared regression, so the the significance index, you will find something that is probably very different from 0. And so if you were naively expecting this estimator here to have the distribution it does have under assumptions of IIDness of observations, you will say that there is a significant coefficient here that relates this time series to the price of your stock. And the problem is that here the assumption about the distribution of this estimator was just really wrong, just because the IIDness of the data was not holding. And more particularly because there was in fact long-range dependence in those two data sets. And so one of the godfathers of econometrics, Granger, actually developed an entire theory which is known today as cointegration or error correction models, that was meant to relate time series that are, for example, like Brownian motions in a way that is statistically significant. So what that means is that we no longer are interested in the correlation between these two time series because as we try to estimate it, under assumptions of cointegration, things work well, but in the general setting, in fact, you cannot rely on any laws such as the law of large numbers. So Granger said, well, I'm going to invent a new particular model in which I have this equilibrium relationship, which I mentioned on Thursday. And I'm just going to require this time that the residual itself is second order stationary, so has, in particular, has short-term memory, although these two time series individually are, for example, Brownian motions. So here there is something that occurs that is rather funny. So although the distribution of R square is not the one that you would expect, and you need a specific statistical test, like the Phillips, it's Phillips-Ulliaris test to check whether this relationship of cointegration actually holds in a statistically sound manner. What happens from the point of view of the OLS is that now if these two time series are actually cointegrated like this, they have individually huge variance. And as you start to find the A and B here that lead to a residual which is itself second order stationary, you will have a residual that has finite variance. And therefore, you have a huge incentive for this coefficient here to find a small residual, and it will be very small in comparison to the variance of each of the individual time series. So that led to, in fact, a concentration here of this estimator, a convergence of this estimator that was faster than what you observe regularly in OLS. So as you had samples here in regular OLS under IIDness of the data, you had 1 over square root of t as a rate of convergence of this estimator to the actual value of the parameter. So it's the rate of reduction of variance, for example. If you have co-integration, now you have a 1 over t. So you have what's called the super convergence in the co-integration setting. So it's just, a side effect of these two time series being co-integrated. It's not really the most important point today to exactly know these two rates. What I wanted to bring up is that as you manipulate objects that have long memory, you need to be extremely careful, because those rules that you knew to be true from your stats 101 class really break down. You have rates of convergence which in some cases may lead to no convergence, and in other cases may in fact help you converge even faster than you would expect from a statistical efficiency point of view. And as we remember, so the kind of time series we look at when we study co-integration are these. These are not even Brownian motion, but you still see that there is. You have these stochastic trends here, for example, that have a very strong directionality, and that's something that radically differs with what you observe, for example, for an autoregressive model. An autoregressive model will just will oscillate all the time. It's time to return to 0 as a finite expectancy. Here you have a process that is radically different. Also, you can see here almost that the amount of memory of the process seems to change with respect to time. Okay, these two processes started the day looking like things that are in fact more directional than Brownian motions, the way they move, and then you start seeing these oscillations, which are more reminiscent of what you have in autoregressive models. And so that's why here we're in fact dealing with a very complex situation, something that is radically different from the usual models we use, for example, in pricing theory in finance. So what I was mentioning here, if you're curious about it, is called spurious regressions in econometrics. So it's basically what not to do when you have integrating processes and you're interested in their pairwise relationships. So when Clive Granger discovered these spurious regressions, and in particular highlighted that the distribution of this estimator here has a radically different shape from what you had in the normal OLS setting, he went on and developed this theory of co-integration and error correction, which devised, in fact, a whole class of equilibria between time series that you observe in econometrics, which, for example, have a unit root, so are roughly Brownian individually, and may have a residual here in an equilibrium relationship that you can study as a process with, for example, second-order stationary properties. So that's basically for the econometric root of this tree that was dedicated to assessing turbulence and long memory in time series. In parallel to that, so there's this theory of the fractal geometry of nature that has been developed by Benoit Mandelbrot. And a corollary, basically, of finding fractal structures in nature was to develop stochastic models that have some fractal properties. And so these models, if you ever come across them, are called fractional Brownian motions. So there are some things, there are processes that are not Brownian motions, but they are not your short-range dependent autoregressive process either. So they feature a certain amount of memory that lies in that intermediate zone, so shorter memory than a Brownian motion, or in fact sometimes even longer-term memory, and still much more memory than what you have in an autoregressive process. In particular, you no longer have this asymptotic independence property, for example. This led Mandelbrot to write a very nice book about how you can apply this theory of fractals and scaling. so self-similarity, which we'll see today, in finance. So the book is very impressive intellectually. The problem is that it's not the easiest to read, speaking from personal experience. So, and I'm probably not the only one to have some issues reading this book. However, I think it's great to try to at least read a couple of chapters, as it really presents a radically different theory if you compare that to the theory of Bachelier, to understand how financial time series move and the kind of dynamics you can try to explain them with. And finally, so the book that I would recommend you read is, actually it's not this one, sorry. So that's the precursor to the book I would recommend you to read, which is really nice, but more an aggregate of articles than really a monograph. And if you're curious about how self-similarity and language dependence relate to wavelets, and how wavelets are really powerful tools to explore such processes, there is this very important article. There's also a lot of research done by Emmanuel Bakri, which focuses on these time series that have different amounts of memory at different points in time. So today, I'm not going to use these more complicated monographs. I will use another one. And before I present it, I would also like to show you that this is not an academic exercise. In fact, the reason why I want to have this lecture is that long-range dependence is pervasive today in the field of time series analysis. So it's long-range dependence is a well-known property of the time series you observe in the analysis of network traffic. So when you have routers, well, for example, the rate of so the number of packets they receive by unit of time, for example, has been proven to be in most cases a long-range dependent time series. You have this article that enabled exploratory data analysis of long-range dependence, and finally these studies in the case of the climate or financial markets that show you that what was observed at some point on Ethernet traffic time series is also true in finance, with the very sad repercussions we've experienced in 2008-9. And to a certain extent still today. So that's for this book here. And we also have a long discussion that is still ongoing in statistical climate science about how we can better assess the individual amount of memory of time series concerned with the concentration of CO2, for example, temperature, but also many other indicators. That has two consequences. The first is to prove much more soundly that there is indeed a statistical effect of the concentration of CO2 on the temperature of the globe on average. The other point is that if you're able to more precisely characterize these statistical properties, then you are able also to have forecasts that could be much more reliable. And therefore, you could plan much more precisely what is going to happen at the scale of the next century. So the presentation I follow today relates to this theoretical monograph, extremely recent, extremely nice to read as compared to the previous ones I presented. And so the short examples that I went through, I believe, lead to the formulation of a question. So it was stupid to try to estimate second-order stationarity related features with Brownian motion, simply because it's not second-order stationary. And so is there a setting in which the law of large numbers will not work, and at which, however, assessing second-order stationary features does make sense? And the answer is yes, and that's the family of processes that I will present to you today. So to formalize the presentation, I first need a mathematical element, which is just the definition of a slow-varying function. And basically, a slow-varying function, just like the logarithm, is this coefficient that, for example, in Landau notation for complexity, you can forget asymptotically, because it varies much more slowly than the other factors in, for example, the time complexity of an algorithm. And so here I will just use the definition of slow-varying function at infinity, which are basically the logarithm is what you should have in mind for that. So things that asymptotically behave very much like a constant, but are not necessarily behaving like a constant. In fact, they may even reach, even go to infinity at infinity. So that's the class of function we are mentioning. And also slow varying function in 0. So you just do a change of variable, and if that inverse, if the inverse parameter leads to a function that is slowly varying at infinity, you get a slowly varying function at 0. So basically, yeah. I will show you the definitions, and basically the intuition is if you see an L like this in a factor, in a convergence rate, for example, don't worry about it, okay? Because in the end, it's a slow varying function that will have much less repercussions on the convergence rate, for example, than the other factors involved. So basically, the L, just forget about it. It's not where the convergence properties are interesting. Yeah, so that leads me to the definitions we can give for a long-range dependence. And so these 5 definitions, I've not seen them presented as such before, so the book by Pipiras and Taku. What is really nice is to understand how they relate to each other, and also what's the intuition behind that. So I start with the historical definition of long-range dependence, which is basically the opposite to the assumption that was made through all the early books on time series analysis. So you see, if you go through a lot of proofs, for example, in the book by Brockwell and Davis or David Bringer, so books that were basically the precursors of time series analysis and were really dedicated to the estimation of ARMA models, that when they want to prove the convergence of an estimator, they start by saying that this sum here of covariances, of autocovariances, is finite. Okay, so one way of saying that we are in another regime than that is just by stating that this sum is in fact infinite. Okay, that relates in fact to the rate at which this function, this covariance function, or equivalently the autocorrelation function, decays at infinitum. So here basically, if your autocovariance or equivalently your autocorrelation does not decay fast enough at infinity, well, that's what you could qualify as a long-range dependent time series. The other definition which relates to that is by in fact really stating, making a statement about the decay rate of the autocovariance or also the autocorrelation function. And so here we see that we have this power law typically. So this decay following a power law for the autocovariance function, which radically differs from what you have in most ARMA models, as in fact you can prove that this rate here, this decay will occur at an exponential rate. So when you have an exponential rate, coming back to this, you know that this sum is going to be finite, okay? However, or if you can bound by an exponential rate of decay. However, when you have this power law, well, now you will have divergence depending on the value you choose for d. All right? So an equivalent, it's not equivalent, but another way, basically a dual way of seeing this autocovariance function is in fact by considering its Fourier transform and therefore taking a look at the spectrum of the time series of interest. And one thing that really differs in the setting of a long-range dependent time series is that if you take a look at the spectrum, so the squared magnitude or the magnitude of the Fourier transform of your time series. Well, if you have, for example, an ARMA model, you will have something that will behave gently, like this, for example. Okay, this spectrum is what will determine the behavior of your time series. But in particular, you can expect these values here to be finite, for instance. If you have a long-range dependent time series, now you will have divergence about 0. And for example, with the Brownian motion, you can even compute the rate at which this amount of energy explodes, about 0. What you can see here is that we are obviously dealing with a process that has a radically different behavior in the frequency domain. And if you remember this definition, this characterization I gave of second-order stationary processes as basically the modulation of trigonometric functions through this, with this spectrum as basically a coefficient scheme. you can see here that in the long-range-dependent setting, you will put a lot more variance, a lot more energy on elements about the zero frequencies and much less energy on high frequencies. So this is an imbalance that is radically different from what you have with well-behaved, for example, short-range dependent processes. So that's the third definition. Actually, how many have I given? Yeah, no, it's fine. Yeah, so now another way of defining long-range dependent processes is to remember a theorem which was true for short-range dependent time series. So if I have this now. And the Wall theorem told you that you could represent such a time series as a rolling average applied to a white noise process. Well, if you can find such coefficients for long-range dependent time series and characterize the amount of serial dependencies through the behavior of these coefficients, then you can get another definition for long-range dependence. So that's this definition, which is basically now a way, in a certain sense, of devising a data generation process and understanding in this data generation process through time which conditions hold on the decay of these coefficients that will lead to the formulation of a long-range dependent time series. Okay? And here, as we could expect, if these coefficients decay at a hyperbolic rate, under some conditions, we will not have this this asymptotic independence, which we really needed for most of our estimation theorems to work.
Is there a typo in the previous one?
Sorry, which one?
You have psi t minus h.
Oh, it's yeah, it's plus infinity. Thank you. Yeah, basically you convolve by this set of weights. Yeah, thanks. Yeah, it's causal indeed. Yeah. And actually, sorry, no, that's, yeah, so you should have phi of h, e of t minus h. That's probably the better way the more readable way of writing it. And the most important definition, which is where you get to when things break down in terms of concentration, is the following, which is basically telling you that now you have settings in which the law of large numbers is no longer true. And so you no longer have a variance of this sum here, which, for example, in the case of IID variables, will just grow in t square. Okay, we have a different behavior. And now we'll have, for example, to think about different normalization factors here. So if I divide by t, here I will have t to the power of 2d minus 1 on the right-hand side. And so in some settings, I will have this convergence, so this decay of the variance that occurs at a slower rate than expected. So now the relationships. So the strongest definition, the most restrictive one, is the following. So the Wall representation of a long-range dependent time series. Okay? If you have this property, you can prove that you'll have all the other ones. So for the spectral density, there is a supplementary condition of monotonicity for the slow varying function that is involved in the definition of the spectrum, but that's just basically a tiny condition. Okay, this is just to show you that basically here we have as expected, as we were redevising a data generation process, a very narrow definition that leads to the other properties that I went through. What is interesting is, well, that if I specify a slow decay of photocovariances, well, the sum of photocovariances will diverge in magnitude, which is, I mean, clearly expected. What is less easy to prove is, in fact, that the law of large numbers will behave in a LRD sense, which means that we won't have the usual decay. So, for example, in t square. So I will go back to that and show you that there is the right way of proving that and a simplified proof that in fact doesn't hold. So just one thing to keep in mind. And then you'll have the same thing basically for the spectral density. As you can see here, we are not going back now to the to the wall representation, though. We cannot get that back with those more general definitions. And yeah, so that's it for the 5 definitions. I think that what I can do now is go through a tiny point about basically how we can get the rate at which the variance of the sum of observations evolves if we have a certain assumption on the amount of autocovariance we have. So we'll start by stating a very simple proposition. So here, here let's just imagine for a second that we have a set of coefficients that behaves as a slow-varying function at infinity times a certain power of k. And here we will assume, we will assume that we deal with integers. So you have a theorem that tells you that under such conditions, if you sum these coefficients up now to a certain so number of observations t, the asymptotic behavior will be so a slow-varying function applied to t, and t to basically the power of p that corresponds to integrating this function, if it was a continuous k, divided by p plus 1 as a factor. So basically, this theorem just tells you that, and I'm not going to prove this one, it's just going to be a tool we'll use. In the discrete setting, if you compute a discrete integral, so this sum here, the exponent you have is the very same as the one you would get with a continuous time integration. Okay, so this is similar to the integral of s from 0 to t of s squared, for example, of sp, sorry, is this 1 over p plus 1 t to the power of p plus 1. Okay, that's just all I have stated. So it's not really surprising. So it's just the first tool. Oh, how can I do that? Oh, yeah, I know.
Is it the same L?
It's a good question, actually. I don't remember. I think so. I'm not sure, to be confirmed. Yeah. So I'm just trying to find a way of. Oh. So now we can actually get to the proof that is actually interesting for us. Okay, so now I'm interested in if I make an assumption on this, so the decay I have for the autocovariance. So for example, I will assume here that so my gamma x of k follows. So let me go back to that. So I will go back to this. So that's my starting assumption. So then what I would like to do is study the variance of 1 over t, the sum of xt for so the temporal index going from 1 to uppercase t. So here, well, if you remember how we prove the law of large numbers, what will happen here is that you have so a t squared that comes up, and then you have the cross products here, which if you compute their expectation, is just the autocovariance function. Okay, because here I made this hypothesis that my time series is second order stationary with that particular covariance structure. So then I'm going to start playing around with my autocovariances. And so one thing I'm going to do is that I'm going to reorganize them. So now I'm going to make my sum symmetrical, and I'm going to express it as a function of a certain lag. Well, basically, so this sum was organized was going from 1 to t here and from 1 to t there. So that was the square over which I was integrating. So now what I can do is, in fact, describe the summation no longer as this square, but as the sum of these diagonals. Okay? So that's all I've done here. I've just made a change of variable. So that's not really the interesting part. The interesting part is what happens when I start splitting the sum. And so already you can see also that a h factor has come up. Okay? So this is what's going to force a certain fast decay of the autocorrelation. If we want to have, for example, this variance here go to 0. So now I have this 1 over t here multiplied by the t in there for h, so going from minus t minus 1 to t minus 1 of the autocovariance function minus the 1 over t squared, the same sum, but this time we have the absolute value of h. And finally, what I do is that I recall so the rate of decay I have for this function, and I apply this proposition. So basically, it's as if I was effectively integrating here. So I'll have a 1 over t L of t, and I was assuming this, so I'll have 2 to the t to the power of 2d over 2d minus the same thing, only I have a 1 over t squared here. And so I'll have L of t, and here I'll have a supplementary exponent because of the absolute value of h. Okay? Actually,
How do you deal with the absolute value?
what was that? Sorry?
How do you deal with the absolute value for the same term?
So here you just need an asymptotic property, right? Asymptotically, you will have this multiplication. Let me just check. I think I'm looking at my lecture notes, and I'm making. I think I made a mistake. Let me just check something. So I don't see the integration come up. That's weird. Oh, OK. Yeah, no, that's right. OK. And sorry, on my lecture notes, I had presented this denominator in there. So then you simplify out. So that's why I didn't have these exponents that were matching. So you simplify out, and you find out in the end that you have something that is basically, you have a certain factor times the slow varying function times this power here that is applied to t. Okay, the t of d minus 1 we had in this should be t minus 1. Sorry. Let me just check something. Yeah, because I normalized by the t. Okay. So if I come back to this definition, sorry. Yeah, in this definition, I did not normalize. So there is a 1 over t squared, and that's why I have a minus 1 here instead of a plus 1.
And again, you just assume that the two L's are same.
Yeah, but here, I mean, it doesn't matter. Okay. Sorry, so I think that a better way of writing this slide would have been to actually put the normalizing constant in there. And there, basically, if you have a 1 over t here, you will have a 2d minus 1 here. Okay? So we just land on this certain decay of the variance, which clearly contrasts with so what you have when you have IID observations. Okay? Sorry, was that?
Are there bounds on D always?
Yeah, because otherwise you will have, for example, some sums that will not behave the way you expect to. So here I assumed this D, for example, to be in 0, 1, or 2. Okay? So yeah, that was basically for this relationship here. Okay. So now the question is, so I was talking about these processes that had longer memory than ARMA processes, and yet not as much memory as the Brownian motion. And one question is, okay, I can characterize the kind of issues that arise if I have those small decays of autocovariance functions. I mean, the hyperbolic decays. One question is, can I construct such a process? How can I come up with such a situation, in fact? So one way of building long-range dependent sequences is, in fact, by considering self-similar sequences. So a self-similar sequence is, you know, one. It's the Brownian motion with a h factor of 1/2. It's a sequence where if you go forward in time, basically, if you dilate the axis of time, you'll find the same behavior up to a certain, so you have a certain constant here, which which carries an exponent, and the exponent characterizes the amount of the degree of self-similarity you have here. So then once you've defined the class of self-similar time series, you can define another family of time series, which is so self-similar processes with stationary increments, which is just this process. And now, so the relationship between LRD, long-range dependence, and self-similarity. So you create an H self-similar an H self-similar time series with stationary increments, with, for example, an H with an appropriate value. You'll find out that the increments themselves are a long-range dependent time series, and they have a certain so they are D long-range dependent, with D having this particular relationship with the exponent H of self-similarity for the integrated time series. So now you basically have a paradigm, a blueprint to create these long-range dependent time series. And also you have a relationship now between the property of basically scaling. So here if you dilate the scale for time, you will dilate also the scale of values for the time series, which is referred to as scaling. So you related this particular kind of time series to long-range dependent time series.
This is done because it's easier to create self-similar time series than long-range dependent.
Yeah, and it's also to build a bridge between two different worlds. So on the top of this picture here, you have, let's say, the fractal community view over a certain class of processes. And here, so the reason why this is fractal is that if you dilate the spatial scale here, I mean, it's time, but it's just an axis, you find that you keep the same behavior, you just have a certain normalization factor, basically. And so there is a tight connection between such processes and long-range dependent time series, which is what I wanted to bring up. Yeah, thanks for the question. Also, now we have an interaction between methods that were designed to, for example, compute the fractal dimension of a certain fractal and the amount of long-range dependence I may have in a time series. Okay? So I'm not, if I have the time, I'll say roughly what a fractal dimension is. The thing is that it's just now broadening the scope of estimators that we can go and use if we want to characterize this long-range dependence. Because if we've really understood now that long-range dependence can create a lot of issues, for example, it can alter the rate at which variance decreases when we have an average-based estimator. One important thing is to be able to characterize the amount of long-range dependence there is. As you can see here, the rate really depends on D. So if I could estimate D, that would be a huge point for me. That would be a huge advantage. And there are multiple families of such estimation methods. I'm only going to present three methods that belong to three different families. So the first one I will present was created by Hurst. So that's why this H exponent is often referred to as the Hurst exponent. And Hurst came up with this characterization of time series that have long-range memory as he was, for example, studying the level of reverse through time. One one aspect that was important in this time series was the rescaled deviations, basically. So here you have the rescaled, actually range, because here you have the span you have for your time series, so the maximum and the minimum, and you just normalize that by the variance. Depending on the amount of self-similarity you have in this time series, this particular feature will take different values. It will behave differently. And so if you have a time series with a certain amount of self-similarity, so h, this rescale range will behave as t to the power of h. So up to, asymptotically, so there will be certain constants. But the thing is that that can still lead you to an estimation method, as if you say that, for example, there exists a constant m such as this relationship is true, you just go to the log, so now you will just have an additive constant. And if you compute a linear regression of the log rescale range onto the log of the time index, the constant that will come up in the affine function, the multiplicative constant, this one we don't care about, will give you the amount of self-similarity you have. The problem is that in practice, this estimator is not the most reliable. You can, for example, imagine how sensitive these max and mins would be to outliers. So that's one of the difficulties that arise if you practically compute this estimator. And I don't know about Python, but these estimators are available in R, for example. There is a package that just does this task. So another way of estimating the amount of self-similarity you have in a certain time series is by taking a look at the power spectrum. As we remember, there was one definition of long-range dependence that was characterizing the time series with the slope of the spectrum about 0. So we expected a certain coefficient here. And so one idea similar to that of the characterization of h with the rescale range indicator is to conduct a regression in log-log scale. We find out that the slope in log-log scale of the spectrum is the h factor plus a certain 1/2. And then we're able as well to estimate the amount of self-similarity and therefore long-range dependence there is for the time series of interest. Another fun way of estimating long-range dependence is this time to really make it, the scaling, sorry, it's more to estimate the scaling really directly, is to make it explicit in a multi-resolution basis. And that's where wavelets come in handy. So if you have a self-similar time series, you basically have a relationship between the amount of energy you'll have and the level of the amount of dilation you impose on your time scale. And if you remember, multi-resolution analysis just studies a time series with different amounts of dilation, and is able to reveal some elements of the time series of interest. One such element is, for example, the self-similarity index. So if you take the wavelet transform of a time series at a certain scale, and so the wavelet is computed at dilated scales. What happens is that if you have a dilation factor lambda here, it will come out in the probability law that characterizes this random variable. And so now one idea is to really focus on the dilation factor here, forget about t, and take a look at the magnitude of the values of the wavelet transform across different scales. So what you can do is, for each scale, so here, sorry, you have lambda and you have time, and you increase your lambda, so you end up with a representation that gets coarser and coarser. You know that basically you'll have a certain progression for the law of your random variable. that will be like this, that will behave like this with respect to the scale. So for example, if you take a look at the magnitude, you can now take the magnitude at different scales lambda, sum the magnitudes of the wavelet transforms through time. So you sum that over t in absolute value. And if you plot these different summed magnitudes, so summed through time across scales, you'll find that in log-log scale, again, you'll have the coefficient h plus 1 over 2 that will appear as the multiplicative coefficient in your OLS. So that's another way of, by characterizing the scaling coefficient, being able to characterize the amount of long-range dependence there is in your time series. There are many other methods. I'm not going to go through all of them. One thing I would like to say, though, is that, for example, a method like the power spectrum method or the wavelet transform method, as the objects of interest can be computed extremely fast with T log T complexity or O of T complexity, well, you have generally computational advantages to using these estimators. This estimator, as I was mentioning, has issues regarding robustness in the presence of outliers, so it's a bit problematic to use it. So now, let's come back to the very first family of models, of linear models I presented in the class, ARMA processes. So what is important about an ARMA process is that it's a very expressive family of functions. In particular, if you have the MA coefficients here, you'll be able, with fewer model parameters, to characterize more complicated dynamics. But the issue is that you can prove that such a process, if it is stable, for instance, will have an autocorrelation that will be bounded by an exponential. And therefore, it will vanish at an exponential rate. You don't have, in such a setting, a long-range dependent time series. Which means that if ever you actually were trying to estimate a long-range dependent time series, then you're probably in trouble. So the way, basically, to take a time series that is long-range dependent and end up with a time series that is not, so that you can actually model them with an ARMA process without having to worry about your model being completely unrealistic, is to apply a certain amount of differentiation to your time series. So if you remember, when you had a Brownian motion, or for example, integrated processes, what we were computing before applying, for example, estimating an autoregression model or computed cross correlations. So the first thing we were doing was computing the differentiated time series. Okay, so for each time step, we would not consider xt, we would consider xt minus t minus 1. So the problem now is that we have an amount of memory that differs from what we get in a Brownian motion. We don't have accumulated sum of an ARMA process, for example. We have an integration that is, in fact, fractional. So I don't have enough time to give the precise definition of fractional integration. However, I can give you the counterpart, so the way to basically take a fractionally integrated process and end up with a process that can be modeled with short-range dependent ARMA processes. So that's fractional differentiation. And if you have this factor d here, if you set it equal to 1, you end up with the classical differentiation. What is nice is that if you have a lower d, now you will be able to erase memory that is still long-range dependent, but less than what you have in a Brownian motion, for example. So you have something that is better tailored to a time series which is long-range dependent. So that's basically a preprocessing step. And one note on this is that it's pretty expensive to compute it. As you see in theory, we would have to go back through the entire path of the time series of interest anytime we want to compute the fractional differentiation for a given time step here. Fortunately, if you want to compute that, you're better off in the frequency domain, for instance, and there you can leverage some properties of frequency domain duality. What is important is that you had so these long-range dependent time series. If you erase their long-range dependence with the fractional differentiation, now you can, for example, calibrate an ARMA model. And so as we were, for example, estimating an ARMA model on the increments of prices, well, we can as well estimate an ARMA model on the fractional differentiates of a certain time series. And that leads to a FARIMA model, which is just a complicated way of saying that now your delta D of your time series is captured by an ARMA model. That's all there is to the FARIMA family. What is super important, though, is that now we effectively have models that can estimate coefficients given by your data in the setting of long-range-dependent time series. And in particular, now we can have predictive models. So to estimate FARIMA models, there are many different methods. I think that the most popular one now is, in fact, by maximizing the likelihood of the model. One caveat, though, is that most of these methods are pretty heavy computationally. And although they work well if you have like hundreds of thousands of samples, the quadratic complexity of the related estimation procedures that intrinsically comes from this fractional differentiation, which needs to take a look really far back into the past. So this quadratic growth of complexity with respect to the length of the sequence of interest makes it very computationally intensive if you have long sequences. So that's just one caveat. If you use procedures that were devised to maximize statistical efficiency and not really computational speed. Yeah, so that's it for the FARIMA model family. You have a broad range of long-range-dependent models. For example, if we come back to the characterization of long-range dependence in the spectral domain, you could imagine that you have a divergence point here, a pole, that is other than 0. And so, for example, you could have something that is like that. And here you have a certain slope. So that leads, for example, to long-range dependent seasonality, which is another aspect that may be important in your time series. So there is really, there should be an entire class dedicated to long-range dependence. As I just have a lecture, now I will just show you the last particular point that occurs when we study such a family of time series. And the last, yeah.
So given a time series, to do fractional differentiation first, how do you estimate D?
So you can use the models. So you can estimate H and then D. But that's not the most statistically efficient way. Although computationally, in particular, if you have a fast procedure to estimate H and then D, therefore, you can, so if you estimate D fast, if you compute this fractional differentiation fast, then you just have an ARMA model to estimate, which is also quick because you just invert a Toeplitz matrix. So if you leverage the fact that these translation invariant operators can be diagonalized in the Fourier domain, you can be doing something great computationally. However, generally, statisticians prefer the likelihood methods because they have stronger guarantees of statistical efficiency. So it's a trade-off. It's actually a pretty important one, though. So the last point I wanted to show to highlight that there is indeed something special going on here when we have these long-range dependent time series, and to come back to the preliminary remark that Benoit Mandelbrot made in this book relating long-range dependence to turbulence. So I would like to show you that if you try to average out perturbations and you have an amount of long-range dependence, the resulting spread about the quantity of interest you're trying to estimate is, in fact, not behaving like a Gaussian. So what I'm taking here is a certain Gaussian time series. Then I will play around with its amount of long-range dependence. And I will just assume that there exists a function f such that this estimated, this variance here of f of xn is not diverging. Okay, so these are just the conditions for the concentration to occur, just to guarantee integrability. Sorry, and so I could ask, well, how this limit here, so this random variable behaves in the limit setting in terms of its distribution. If I'm in the classical setting of IID variables, I know that this will behave with the conditions I have on f. Actually, there should be an f. Sorry. I should have a Gaussian. So the question now is, what happens if my processus xt is not IID, and in particular, what happens if it has a certain amount of long-range dependence? So What is interesting here is that there is in fact an interaction between the amount of memory you have in your process and certain properties of the function f here, which refer to its Hermite rank. So I won't bother you with what the Hermite rank of a function is. Plus, it's a notion here that is only relevant because we are studying Gaussian stationary time series. What is important here is that you remember this as an example where we take a certain sum normalized properly, and we should normally have convergence in law, so in distribution, to something that is Gaussian. And in fact, I mean, normally that means in the short-range dependent setting. Here we find out that the limit distribution is radically different. And by different, I mean it's an Hermite process. The only thing you need to remember is that this Hermite process is not the usual Brownian process, which corresponds to the Gaussian distribution you have in the general central limit theorem. So here you end up with what is called a non-central limit theorem that tells you that asymptotically, although you may effectively converge to a certain distribution for this variable, now you may have a spread of values that is non-Gaussian, and which means that in some settings, for example, you will get these fat tails, so those huge deviations which really lead your system to a catastrophic state. And that's, for example, a principle that is thoroughly studied in the field of econometrics, where some researchers are trying to prove that one of the elements that make financial crisis so bad is that investors behave in a herding way. And therefore, when there are perturbations, well, you have a certain amount of non-independence through time that will push your system much further away from its, for example, equilibrium state than if you had perturbations that are independent and will therefore average each other out. If you have a certain amount of memory in your system, you will not have this averaging mechanism, and therefore it could really lead to large deviations. So that's one way of trying to explain those large deviations that we see in the real world and don't really fit well within the, I mean, they, for which models that are inherited from the field of thermodynamics do not really fit well. Because mostly in thermodynamics, what led to these like Gaussians was the inherent assumption of dynamics at the microscopic level having perturbations that are independent and therefore average out. Here, when we have, for example, humans in the loop, well, humans are not atoms that oscillate, for example, mindlessly. Humans react to what they've just seen and they're going to adapt their behavior accordingly. Okay, so that's just why in practice, for example, in financial markets or also on systems such as that involve recommendations, this adaptiveness of smart human beings leads to a law of concentration that is different than the Gaussian. So just to conclude the lecture, be extremely careful when you don't have asymptotic independence. We may have very subtle cases in which it does make sense to try to estimate second-order properties of a certain time series, but in fact cannot really in the straightforward way. We do have a reduction of variance that follows a different kind of decay than what we have in the IID setting. In some cases, we just don't have any reduction of variance. And if there is LRD, it can be adverse to you, but it can also be used so as to get better predictive ability. So if you have an amount of memory, for example, for a certain financial time series that is higher than the Brownian motion, now it means that your market is not efficient. If you have basically perturbations that are positively autocorrelated, you can use what are called stochastic trends, which this could be an example of that. So basically, if you're able to detect them, could tell you, well, here you actually have a less efficient market setting, so go ahead, you can follow the local stochastic trend as a good predictive rule. Yeah, that's it for today. Thank you.
Hold on. I just want to mention that next week, François, you cannot hold office hours.
Yes.
So I'll be holding those office hours with less expertise.
Oh.
So I propose that you come in with project-related questions and stuff like that, but